Okay, let's just jump right in. If you've ever looked at AI and thought, wow, that's just pure magic, or maybe that's an impenetrable wall of math, well, you are in exactly the right place. Today, we're doing a complete explainer on machine learning's most fundamental engine. We're talking about linear regression. Relying on insights from Andrei Burkov's The 100-Page Machine Learning book, we're going to unpack a little secret from the preface. You see, machines don't actually learn the way that you and I do. What they really do is find a mathematical formula that produces desired outputs for a given set of inputs. And today, we're going to look at exactly how one of the most absolutely crucial of those formulas is built.
We're actually going to kick things off with a brilliant quote from statistician George Box, because it honestly sets the perfect philosophical stage for us. He said, "All models are wrong, but some are useful." I love that. In machine learning, we aren't looking for absolute mathematical perfection that captures every single tiny nuance of the universe. No way. We're looking for practical utility. We want a model that's useful enough to make accurate predictions on totally new data. So definitely keep this in mind as we build our model today. We are aiming for a really useful abstraction of reality, not a flawless mirror.
So the crucial starting point is understanding what regression actually is, even before we get to the linear part. In the machine learning world, regression is just a problem of predicting a specific, real-valued label. We usually call that a target. This is totally different from classification, where you're sorting things into buckets like spam or not spam. In regression, we want a continuous number. We feed the machine an unlabeled example, and we're essentially asking it to spit out a highly specific real number based on what it's already learned.
To ground this in reality, just think about trying to predict a house's price. You wouldn't just guess a price out of thin air, right? You'd look at the house's specific characteristics, its area in square feet, the number of bedrooms, the exact neighborhood it's in. In machine learning, we call this collection of characteristics a feature vector. It's literally the real-world data we feed into our model. Every single example in our dataset has this feature vector, and we use these features to try and predict that final, real-valued target, the price of the house.
And here is the engine itself. This equation right here is the absolute mathematical heart of linear regression. Our model, which is denoted as f, is parameterized by two values, w and b. Actually, to keep it simple, it's just a linear combination of our features, which are represented by x. Now, let's translate that math. In this equation, w is a vector of parameters. To tie it back to our house example, think of w as the weight, or the specific price value added by each individual feature. Like, the actual monetary value of adding an extra bedroom. And b, that's just a single real number, a baseline. Think of it like the starting price of a completely empty lot. Our linear regression model uses this exact formula to try and get as close to all the training examples as humanly or mechanically possible.
Now let's see this math actually come to life. Those dark blue dots you're looking at are our training examples. Each dot represents a piece of data where we already know the answer. It's like a past house sale where we know both the features and the final sale price. And that light blue line? That is our linear regression fit. It's the visual representation of that wx plus b formula we just talked about. Notice how the line doesn't perfectly touch every single dot. Instead, it strikes a balance. It's drawn to stay as close to all the dots as possible. This single line is what we're going to use to predict the target for any new, completely unseen data we encounter down the road.
But this raises a really fascinating question. How on earth does the machine learning algorithm know exactly where to draw that line? I mean, two different models with two different sets of w and b parameters are going to draw two completely different lines, producing totally different predictions. We absolutely need the optimal values to define the model that makes the most accurate predictions. So, how does the machine objectively decide that one line is better than another?
Well, it does this by calculating the cost of its own mistakes. When the machine draws a line, it measures exactly how far off that line is from the actual known training dots. We use something called a loss function to measure the penalty for these mistakes. Specifically, for linear regression, we use the squared error loss. We take the predicted value from our line, subtract the true target value, and then we square the result. This gives us a mathematically rigorous penalty for every single time the line misses a data point. And because we're squaring the difference, this method actually punishes larger mistakes way more heavily than smaller ones.
And this brilliantly illustrates the whole entire goal of our algorithm. We aren't just looking at one mistake, we're looking at all of them at once. Our optimization procedure aims to minimize what we call the empirical risk, which is basically just the cost function. This is simply the average of all those squared error loss penalties across our entire set of training data. The algorithm just tweaks those W and B parameters over and over again until that average penalty, that empirical risk, is as low as absolutely possible. And boom, that is exactly how the line finds its perfect fit.
Now, I want to share a wildly surprising piece of history with you. We tend to talk about machine learning like it's this completely modern marvel of the digital age, right? But the sum of squares method we use to optimize this cutting-edge math, it was actually first published way back in the year 1705. Yeah, 1705. It was introduced by the brilliant French mathematician Adrien-Marie Legendre. So the foundational logic driving our highly advanced predictive AI today has basically been sitting quietly in mathematics textbooks for over 300 years. Crazy, right?
But you might be wondering, why did Legendre choose to square the error? Actually, why not just use the absolute difference, or even cube it? Well, you see, the absolute value is actually incredibly inconvenient for optimization. It doesn't have a continuous derivative, meaning it's not a smooth function. But by squaring the error, we get this beautifully smooth, bowl-shaped curve with a continuous derivative. This means that instead of just blindly guessing, the computer can essentially roll down the sides of this curve to easily find the absolute bottom. That bottom is the exact point of lowest penalty. It literally allows the computer to calculate the optimal solution super efficiently using simple algebra.
And this builds into a critical choice that every single machine learning engineer has to face, choosing between a simple straight line and a highly complex model. You're probably thinking, hey, if our goal is to minimize errors on our training dots, why force the model to be a stiff straight line? Why not just use a complex polynomial equation that can bend and curve to hit every single dot perfectly? Well, it turns out, giving a model too much flexibility is hands down one of the most dangerous traps in all of data science.
Take a look at this wildly swerving red line. The data points here are exactly the same as the ones we looked at earlier, but instead of a straight line, we're using a polynomial regression of degree 10. And look at what it does. The red line swoops and dips to perfectly touch almost every single dark blue training dot. The squared error loss on the training data here is practically zero, but this perfectly illustrates a really problematic phenomenon called overfitting. While it memorized the training data flawlessly, look at how chaotically it behaves in the empty spaces. If we gave this model a brand new piece of data to predict, it would likely make a massive, catastrophic error. It's curving dramatically just to chase the random noise in the old data.
And this proves exactly why linear regression is so universally valued, despite being so incredibly basic. One practical justification for the linear form is simply that, well, it's simple. Why use a complex model when a simple one gets the job done perfectly well? But the deeper, more important consideration is that linear models rarely overfit. By mathematically restricting the model to a straight line or a flat plane, we physically prevent it from obsessing over the tiny quirks and random noise of the training data. It learns the general trend instead. And that means it remains genuinely useful for real-world predictions on data it has absolutely never seen before.
We started out by acknowledging that all models are wrong, but some are useful. By calculating the squared errors of our past data and finding the simplest possible line that minimizes those mistakes, we create a tool of just immense utility. So I want to leave you with this thought to ponder today. If we can reliably predict something as highly variable as house prices, just by using an algorithm from 1705 to draw the perfect line through past errors, what other complex mysteries in our world could be solved this simply? What patterns are hiding right in plain sight, just waiting for a straight line to connect them?